This is the output of a circuit I just made, whose purpose is to simulate the shape of mammalian action potentials, or at least cortical mammalian action potentials. Action potentials are depolarizations that depolarize and repolarize very quickly, and they have a little bit of a overshoot, which is called an after hyperpolarization. So it's slightly more hyperpolarized after the action potential than before it, and that slowly goes back to baseline over a little bit longer period of time. And together this is called the after hyperpolarization, or AHP. And this action potential generator is firing at about 6 hertz. I think we can actually measure that. Yeah, you look at the frequency, we've got 6 hertz. And the cool thing is that this circuit is realized using entirely analog circuitry. So this is the circuit that I made, and I'll walk through it in a minute. But first, let's just kind of summarize how this works. Up top, I have 12 volts coming in, and I have a LM7805 linear voltage regulator with some capacitors here to smooth out the output. But this circuit is entirely powered by 5 volts. There's a 555 timer I see here, and then we have a few decoupling capacitors, a couple diodes, a bunch of resistors, and some NPN. We actually just have 2 NPN transistors. And then the output is decoupled through a series capacitor and goes to my oscilloscope. So how are we actually generating this? Well, let's step through the circuit, which I have drawn out here, and then we can look at the simulation on the computer. Okay, so just to summarize again, an action potential is characterized by a very quick depolarization and repolarization. It overshoots its initial voltage by a little bit, and that slowly recovers. And together this is called the AHP, or the after hyperpolarization. So there are alternative neuron simulator circuits, which are actually a little bit more physiological. They have voltage-activated currents, which mimic voltage-activated ion channels, which exist in cell membranes. But those circuits are a little bit more complex, and they do have some self-firing behavior. But I desired to have a circuit which could be triggered by square waves. And the reason why is I can envision more complicated applications where perhaps I would have a random square wave generator, which generates square waves at random times, and then produces randomly timed action potentials, which would be a little bit more difficult if I used the intrinsic circuitry to initiate action potentials. And there are some other reasons. I just decided to do it this way as an exercise, and the result came out pretty nice. So the first step in generating these action potentials is we need some square waves, and I generate that with a 555 timer. And if you Google around, this is a pretty simple circuit. It uses the ratio of these 2 resistors and this capacitor value to generate a potentially variable frequency of square waves with a variable duty cycle. And if we wanted to adjust the frequency of action potentials, we could do that by adjusting this resistor here, or the value of this capacitor. So this circuit could be just by adding a variable resistor or a potentiometer here. You could have a knob so you can change the action potential frequency, which would be pretty cool. So the output of this 555 timer comes out here, and actually let's go ahead and hook that up. So I've got a second oscilloscope probe attached to the output of the 555 timer, and I'll turn on channel 2, and in this blue trace you can see what the output of the 555 looks like. Every time you have a rising edge, there's an action potential. And the way I'm generating my action potential is by isolating the rising edges of the output of the 555 and then doing a little bit of wave shaping. So there's a fast positive component, and there's a slightly slower, smaller negative component. So let's take a look at that. So we've got square waves coming out here, and then they're decoupled through a series capacitor, and then we have 2 additional series capacitors. So from this point on, we have 2 separate signals which are handled differently. And this signal generates a faster pulse, which gets turned into the positive pulse. This lower one generates a slower pulse, which is turned into the negative pulse. And we mix the positive and the negative pulse here with a resistor divider, and the difference in the resistances means that our positive pulse will be more profound than our negative pulse. But we mix them here, decouple finally with 1 series capacitor, and then we take the output here. So here, consider we have a square wave coming in, And then when you look at a square wave through a small value series capacitor, a square wave, which would normally look like a square, it comes out to be little tiny points almost. And a rising edge creates a positive deflection, and a falling edge creates a negative deflection. And then when we use a series diode like this, we capture just the positive deflections. So by this point here and here, we're only having a flat line with positive deflections every time there's a rising edge. And we can make those positive deflections last a little bit longer by changing how quickly they drain back to ground. So I have a drain resistor or a leak resistor here, which takes that positive current and it brings it back to ground. There's a little bit of capacitance in this line, although it doesn't have to be added with an actual capacitor. There's a little bit of capacitance here between the base and the emitter of the NPN transistor, and also in the wire and in the lines themselves. So that little bit of capacitance is all it takes to cause that little rising pulse to slowly decrease. And by having a different value resistor here and here, I can cause this pulse to be faster than this pulse. The larger resistor down here makes it drain slower, so this is a little bit slower pulse. So again, I want my fast pulse to be positive and my slower pulse to be a negative current, and I use a NPN transistor amplifier, really simple, and I use it the same way, but I take from opposite parts of the transistor, so that they've both got a 1 kilo ohm resistor on the emitter and the collector. And here I just take from the emitter to get my positive pulse, and here I just take from the collector to get my negative pulse, and then I add them together and I have a circuit that produces this output. And we can also check this out in software. So here I'm using ltspice, and this is free software that lets you design circuits and simulate them to see how they would operate if they're built. There's a little bit of a difference between how they actually perform in real life compared with how they're simulated, and it has to do with those stray capacitances that I talked about earlier. So let's take a closer look here. The only real thing we need to look at is the difference between this top point here and this point here. So like I said, actually let's back up, I guess. There's our square wave coming in. When it goes through a series capacitor, it looks kind of like this, pretty similar. After going through the diode, it only captures the rising edge, and the difference in these resistors is what causes this one to be a longer pulse and this one to be a shorter pulse. And keep in mind that in my paper version, I put the slower pulse on the bottom and the faster pulse up top, and they're inverted here. So here's a slower pulse and here's a faster pulse. And yeah, so let's look at the output of the transistor. Here's that longer pulse, and I collect on the collector, or I capture the voltage on the collector. So every time you get a positive pulse, it's this downward deflection, which is going to become my AHP. And if I look down here, we have the opposite. We have a very fast, large upward deflection from the shorter pulse. And I can combine them here and run it through a decoupling capacitor on the output, and I get something that looks a lot like action potentials. So between our simulation, our circuit design, everything makes sense here, and they come together on the breadboard to make an output which looks enough like an action potential that we can do some other additional experiments, such as derivative detection and peak detection and that type of thing. So all in all, there's a really quick, simple circuit to produce a waveform that looks close enough like an action potential. So I had an idea of one more thing I wanted to try. I'm going to use a stereo cable where I've cut off one of the ends and exposed the wires. And I have access to the ground and the left channel input. And I'm going to record the output of the circuit into my computer using the sound card. So I'm just going to go ahead and plug this into the microphone hole of my computer. And then here I'm going to clip ground to ground, and I'm going to clip the output of my circuit, which is normally going to my oscilloscope. I'm going to clip there and just clip it onto the left channel of the microphone. And the reason I use the left is because if you do a mono recording, then it sometimes just takes from the left channel. So let's take a look at computer here. Okay, yes, I just plugged in something. I'm going to open a program called Goldwave. Goldwave is free software and it makes it easy to do audio recordings. I'm going to make a new audio recording, 14 kilohertz mono, that's fine, and I'll just hit record. And you can see there's some up and down fluctuations here. That's because of the action potentials. And I'll just let it finish its thing. And then the problem now is that the voltage is really small. It can take a higher voltage on the input. So instead of increasing the voltage output of the circuit, let's just do it in software. We can do volume, maximize volume. And that will make the action potentials take the full span. And if we zoom in, you can see there's the rise and the fall of each action potential. So that's pretty cool. I can save this as a wave file, and I'm not going to go ahead and duplicate it. I've already done that. Okay, so I have this wave file here, and then I've also written a Python program called analyze.py. So let's just take a quick look at that. I'm going to use the Spider Python editor, or the IDE. And this is what's in the program. So just super quick to summarize it, it imports some libraries for handling numbers and for graphing. It then loads the recording file. And wave files are pretty easy because I'm using a 16-bit wave file, so I can just read data directly from the file name using this memory map function. And I'm not going to talk about it any more than that. I skip a little bit of the beginning of the array because there's some header information, and then I only capture the first few seconds. And then I do a scaling adjustment that takes my action potentials and it makes them look like they would be in a human body or something, resting at about minus 70 millivolts. And then I generate a time axis, and then I make my figure and do the plotting. So here I make my figure, I add a grid, I actually plot the x's and y's, I adjust the margins so there's a little bit more space vertically than horizontally at the end, and then I add my labels, and that's pretty much it. So I'm going to use the Python console here to run this. And this is some of the data that we recorded from our wave file. And this is using matplotlib, so these graphs are interactive. But it's pretty cool. You can see really clearly the rise and fall of these action potentials, and they're centered at about -70, which is kind of what we would expect. So I'm just going to have savefig run instead of show. I run it once, and now I've got graph.png, and there's the output of our circuit.